Following on from the previous video, we were trying to differentiate x to the power of a fraction. So we would write x to the power of, we would write it as x to the power of m over n, where m and n are integers. So we were trying to differentiate this here without moving this down to here, and then this itself gets minus by 1. We've got to differentiate this here without making that move, because we are trying to show that that move is legitimate. So we cannot use that move to show that that move is legitimate. So we've got to be able to differentiate this here without making that move. So the way we do that is to exponentiate both sides. So that will then give us this here, and then this here gets multiplied with this, and then at the end of the previous video we got to this stage here. Okay, we got to this stage at the end of the previous video. So now now you would use implicit differentiation here. Implicitly differentiate both sides. The thing is, you can do it here, but you couldn't do it up here, because if you try and differentiate up here, you've got no choice but to move this down here and then take away this. But the thing is, we're trying to show that this move here is legitimate. We're trying to show that this move here is legitimate. So we cannot make this move here. That's why we have to exponentiate both sides to take it to this stage, and then from this stage here, take it to this stage here. So now when we're at this stage here, we can simply do this move, because remember, up until now we've shown that we can differentiate positive whole numbers and negatives, but we just don't know for sure that we can do it in a case of a fraction. You see, something like this we don't yet know how to do, but this here we do know how to do it. We've proved that this one here, when it's a whole number, negative or 0, we can just simply move it down here. This we know how to do. This we don't yet know how to do. We're trying to show that we can do this. So that's why from here we would exponentiate both sides to get it from here, and then from here we would move down to here. So now you see, this here is like a whole number, this here is a whole number. We can do it. Up here is a fraction. We don't know how to do it. Well, anyway, from here use implicit differentiation. So differentiate both sides. So remember, you've got to imagine y is a function of x, so you've got to imagine this as being a bubble. So this here, remember, this here is a whole number, so we can make this move. So that then becomes n y, the bubble itself intact, and then n to the power of minus 1. Because y is a function of x, you've got to stick this dy by dx in here. Okay, so use implicit differentiation to get from here to here. To get from here to here. So when you come to differentiate this, m is a whole number. Now we know how to differentiate whole number. We can just simply move it down here, and then the m here itself gets minus by 1. Okay, so that would then take us to this stage here, and then isolate the dy by dx here. So divide both sides by this thing here. That would then give you this. Okay, and then remember from indices that whenever sorry, hang on. So from here, that will then take you to this stage here. Okay, so dy by dx equals this thing here. But the thing is, you want dy by dx in terms of x. So you don't want this y floating around inside your answer. So from the start, remember, from the very start, our aim to differentiate x to the power of a fraction. So right from the start, y was this here. So we can simply put this into this y here. Okay, so hang on. So we got to this stage here. Use implicit differentiation to take us to this stage here, and then isolate the dy by dx. That's because we want to work out what dy by dx is. So we would divide both sides by this thing here. That would take us to this. So the answer is dy by dx equals this thing here. But then you've got a y floating around here. We want the answer in terms of y. So y, right from the start, y equals this here. So put this into the y here. So that would then give us this. Okay, that would then give us this. So now it's this times this, because remember, because x to the power of a to the power of b, then you just, well, it's just us tidying this bit up. So this times this here would give you this. Hang on, yeah. Sorry, I'm saying one thing but doing another thing. So so from here, factor out. Well, not just remove this thing here, because at the moment you've got one block. At the moment you've got one block multiplying with this block here, multiplying with this block here, multiplying with this block here. So let's cut this fraction up like this. So you've got m over n times this thing here. Okay. So from here you would get to here, and then remember, from if you have a over b to the power, if you have x to the power of a to the power of b, that becomes, well, a times b here. So now we're going to get this times this thing here. Okay. So yeah, this is what I was saying earlier. So it's just a matter of getting this multiplying with this. Well, we are just trying to tidy up this bit here. We are just trying to tidy up this bit here, because you've got x to the power of something to the power of something. So you can just simply multiply the two together. So multiply the two together, that would give you this. Okay. So this bit here. So this bit here is going to be this. Okay, so basically, hang on. So we were here. We're just going to merge these two together here. These two together, merge them together. It will give you this. Okay, it will give you this here. Okay, so now hang on. Let me think. Now remember that when you have one thing divided by another thing. So when you have x over, so here you're just going to get a take away b here. So we're just going to get this thing take away this thing. So that's this thing here take away this thing here. So that would then blah 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 here, tidy this up here. So that would then give you this here. Okay, this thing take away this thing equals this thing here, and then that simplifies to that. So when you get this take away this here, it then becomes this. So you've got this thing multiplying with x to the power of this thing here. Okay, and notice here, hang on. So our final dy by dx equals this thing here. So hang on. So originally we started out with this, and then we got to this stage here. By the way, this stage here is this thing here. Okay, so it's just the same thing here. So we started out with this, and then when you come to work out dy by dx, it equals this thing here. Now look at this here. When you want to differentiate this, look at this. This is like a bubble. It gets moved down to here. That's this bit here, and then the bubble itself gets minus by 1. The bubble itself gets minus by 1. So we started out with this thing here. We got to this thing here, but then you can see from here that that you can just simply move this down here, which is this bit here, and then the power itself here gets minus by 1. The power itself here gets minus by 1. You see, we did it without, we use implicit differentiation to get from here to here. And when you get to this stage here, you can see that whenever you have x to the power of fraction, you can just simply move this down here, which is this, and then get this minus by 1. Okay, so we've now proved that it works for all fractions. When you have x to the power of fraction, any fraction, you can just simply move this down here, and then the fraction itself gets minus by 1. Okay.